Wow, this is quite the collection you brought together on marine diesel engines. I'm excited to really get into this with you.
Yeah, it looks like we've got pretty much everything here, huh?
Looks like it, yeah. I mean, we're talking the full range here, from the basic science behind how these things work to the nuts and bolts of the engines themselves and even how to keep them running smoothly.
You've even got some stuff on the latest developments in the field, which is always interesting to see.
Exactly. So let's see if we can distill this all down, help our listeners really understand what makes these massive engines tick.
Sounds good to me.
Okay, so how about we start with the absolute basics? Like how these engines actually convert fuel into the force that propels these huge ships.
Sure.
Your sources talk about this process of energy conversion, right?
Right.
Starting with the chemical energy locked up in the fuel,
Yeah.
and then transforming that into sensible energy, which is basically heat, right?
hmm
And then finally channeling that heat into mechanical work, the actual force that turns the propeller.
That's the gist of it, yeah. It's all about harnessing that energy and turning it into something that can actually move a ship.
It's pretty amazing when you think about it. I mean, the sheer scale of these engines is incredible.
It is, yeah. And the amount of power they generate is just mind-boggling.
Absolutely. So to understand how that heat energy gets translated into motion, we need to delve into some basic physics, right?
A little bit,
Like
yeah.
those gas laws I'm sure you came across in your research.
Oh, yeah, those are always fun.
Okay, well, there's Boyle's law, which states that the pressure and volume of a gas are inversely proportional when the temperature is held constant.
Basically, if you squeeze a container of gas, the pressure goes up.
Right. And then we have Charles's law, which says that at constant pressure, the volume of a gas increases proportionally with temperature.
So heat it up and it expands.
Exactly. And if you combine those two laws, you get the characteristic gas equation, PV equals RT.
Where P is pressure, V is volume, R is the ideal gas constant, and T is temperature.
Right. And this seemingly simple equation is actually fundamental to understanding what's going on inside the cylinders of these engines.
It really is. It might seem like basic stuff, but it's the foundation for everything that follows.
Okay, so building upon those fundamental laws, we have the different thermodynamic processes that actually govern how those gases behave inside the engine.
Right, we've got isothermal processes where the temperature stays constant,
Then there are isochoric processes, which happen at a constant volume,
and isobaric processes where the pressure is constant.
and adiabatic processes where there's no heat exchange with the surroundings.
Right, and in reality, these engines usually operate under polytropic conditions.
Meaning,
A combination of heat and work transfer is going on.
okay, and grasping how the pressure, volume, and temperature change during each of these processes is key to understanding the engine's efficiency and performance, right?
Absolutely. I mean, it's all interconnected.
Now, this brings us to the engine cycles themselves, the actual sequence of events that transforms fuel into that propulsive force.
Right.
The four-stroke cycle is obviously a major player here.
It's the most common type, for sure.
And I'm guessing you already know the four distinct phases: suction, compression, power, and exhaust.
Yeah, I think we've got those down.
All right, but let's break them down anyway, just to make sure we're all on the same page.
Okay, sounds good.
So first up, we have the suction stroke. What exactly is happening here?
Well, the piston moves down, creating a lower pressure inside the cylinder.
Right, and that pulls in fresh air through the open inlet valve.
Exactly. And once the cylinder is filled with air, the inlet valve closes, sealing everything up.
Okay, so we've got our air, and now comes the compression stroke.
Right. The piston moves up, and with both valves closed, it squeezes that air into a much smaller space.
And this does what to the pressure and temperature?
Well, the pressure skyrockets. We're talking up to 32 to 45 bar.
And the temperature.
It goes way up, too, somewhere around 600 to 700 degrees Celsius.
Wow, that's hot. So at this point, the fuel is injected, right?
Right at the peak of compression. And the heat ignites it almost instantly.
Boom. And that leads us to the power stroke, the heart of the whole cycle.
Exactly. The combustion creates this massive pressure increase, forcing the piston back down with a huge amount of force.
This is where all that chemical energy stored in the fuel is finally converted into the mechanical work that drives the ship.
Right. It pushes on the crankshaft, which ultimately turns the propeller.
Now, we can't forget about the final phase, the exhaust stroke.
Of course not. That's where we get rid of all the burnt gases. The exhaust valve opens, the piston moves back up, pushing those gases out of the cylinder, making room for the next cycle to begin.
Okay, so that's the basic four-stroke cycle. Now, Your sources also mentioned something called valve overlap.
Ah, yes. That's an interesting little detail, especially when you're dealing with turbocharged engines.
So what's happening there?
Well, the intake valve actually starts to open a bit before the exhaust valve fully closes.
Why would you want to do that?
It's all about getting a better flow of gases through the cylinder, especially in turbocharged engines, which have a much more pronounced overlap, sometimes as much as 120 to 140 degrees of crankshaft rotation,
Compared to?
compared to naturally aspirated engines, which might only have 30 to 50 degrees of overlap.
So what's the advantage of this greater overlap?
It improves what's called scavenging. Basically, it helps to completely clear the exhaust gases out of the cylinder.
It's like the engine is taking a deeper breath.
Exactly. The incoming fresh air pushes out the remaining exhaust, and it can also have a cooling effect on things like the cylinder head and the piston crown.
Okay, and I'm guessing this is all carefully timed out, right?
Absolutely. Your sources probably have valve timing diagrams showing the precise sequence of events, and you can see how they differ depending on whether the engine is turbocharged or naturally aspirated.
So we've talked about the four-stroke cycle in detail, but you also mentioned the two-stroke cycle as another way to get power out of an engine.
Right, the two-stroke is kind of like the four-stroke's more compact cousin. It does the same job, converting fuel into power, but it does it in two piston strokes instead of four.
How does it manage that?
It combines the intake and compression steps into one upward stroke, and then the power and exhaust steps happen during the downward stroke.
Clever. And those two strokes often use ports in the cylinder liner instead of valves, right?
That's right, the piston itself covers and uncovers these ports to control the flow of air and exhaust gases.
Okay, so while two-stroke engines are definitely out there, it seems like four-stroke engines are the real workhorses in the marine world.
Yeah, especially when it comes to those massive container ships and tankers, the four-stroke is generally more efficient, especially at the larger scales.
Okay, so now that we have a good grasp of these real-world cycles, let's talk about the theoretical limits of efficiency. And your materials mentioned something called the Carnot cycle.
Ah, yes, the Carnot cycle is like the holy grail of thermodynamics.
In what sense?
Well, it represents the absolute maximum efficiency that any heat engine could possibly achieve.
Really? But it's purely theoretical, right?
It is, yeah. It involves two isothermal processes and two reversible adiabatic processes, which you can't perfectly replicate in a real-world engine.
Okay, so why even bother with it then?
Because it gives us a benchmark. It tells us what's theoretically possible. The Carnot efficiency is calculated as 1 minus the ratio of the absolute temperatures of the cold reservoir to the hot reservoir.
So the greater the temperature difference, the higher the potential efficiency.
Exactly. But again, we can't actually build an engine that perfectly follows the Carnot cycle.
Too bad.
Yeah, but it's still a valuable concept.
Okay. Now, your sources all of them mention the Otto cycle.
Right. The Otto cycle is the theoretical model for spark ignition engines like the ones you find in most cars. It's characterized by constant volume heat addition.
Okay, and what about the big marine diesels we're focusing on here? What cycle do they typically operate on?
Well, those rely on compression ignition, meaning the heat generated by compressing the air is enough to ignite the fuel.
Right, no spark plugs needed.
Exactly. And these diesel engines often operate on what's called a dual combustion cycle.
Which is?
It's a combination of constant volume and constant pressure heat addition. And you find it in both two-stroke and four-stroke diesel engine.
Okay, so it's kind of a hybrid cycle?
You could say that, yeah. And in terms of efficiency, it falls somewhere between the Otto cycle and the theoretical diesel cycle.
So it's a good balance of power and fuel economy for these heavy-duty applications.
Exactly.
Okay, we've covered the fundamental principles and the cycles themselves. Now let's get into the actual physical structure of these engines, the nuts and bolts, so to speak.
Let's do it.
Your materials provide detailed lists of the components for both two-stroke and four-stroke engines. And we see some common elements like the bird plate, crankshaft, camshaft, cylinder liner, piston, and connecting rod.
Right. Those are the core components that you'll find in pretty much any reciprocating engine.
But two-stroke engines also have some specialized parts, right?
Yeah, like the A-frame, the entablature, the piston rod, and the crosshead.
Okay, so let's start with the bed plate. What's its role in all of this?
The bed plate is essentially the foundation of the entire engine. It's this massive, incredibly strong structure that everything else is built upon.
Okay, and what does it actually do?
Well, it houses the main bearings that support the crankshaft, and it supports the whole cylinder block assembly above it.
It has to be incredibly strong and rigid, right?
Oh, absolutely. It has to withstand the huge forces generated during combustion and keep all the moving parts precisely aligned.
And how is this enormous engine actually attached to the ship itself?
Ah, that's where the holding down bolts and chocks come in.
So what do those do?
Well, the holding down bolts are these incredibly strong fasteners that clamp the bed plate to the foundation plate, which is part of the ship's whole structure.
Okay, so they're basically bolting the engine to the ship.
Pretty much, yeah. And the chocks are these precisely machined pieces that fit between the bed plate and the foundation plate.
And what do they do?
They help to accurately position the engine and make sure it's properly aligned with the propeller shaft.
Because if it's not aligned,
You'll get uneven wear on the bearings, and that can lead to all sorts of problems.
not good. And I see that there are different types of chocks, solid and resilient.
Right, solid chocks are usually used in large, slow-speed, two-stroke engines.
Because,
Well, because those engines are so massive and generate such huge forces.
okay, and resilient chocks.
Those are more common in medium and high-speed engines.
Why the difference?
Resilient chocks are made from special materials that help to dampen vibrations,
Which is important for?
for reducing noise and wear and tear on the engine and the ship's structure.
Now, you mentioned that the bed plate is bolted to the foundation plate.
Right.
And what about tie rods? What are those for?
Tie rods are these long, high-strength bolts that run vertically through the engine's structure.
And their purpose?
They put the entire engine structure under compression.
So they're basically squeezing the engine together.
You could say that, yeah, and this pre-compression does a couple of important things. It makes the engine much more rigid, which helps to prevent fatigue failures.
Okay, and?
And it helps to maintain the alignment of all the moving parts.
So just like with the holding down bolts, any slack in the tie rods is a bad thing.
Absolutely. You want those tie rods to be properly tensioned. Otherwise, you could get flexing, fretting, misalignment, and all sorts of other issues.
Right, so regular inspection and tightening are crucial.
For sure.
Okay, let's move up into the engine itself now, and let's talk about the pistons.
All right, the pistons are the workhorses of the engine. They're the ones that take all that heat and pressure and translate it into motion.
And they're subjected to some pretty extreme conditions, right?
Oh yeah, we're talking incredibly high temperatures, pressures, and corrosive environments.
So what are they typically made of?
Usually, you'll find them made from cast or forged steel.
And those materials have to have some pretty specific properties, right?
Right, they need to be strong at high temperatures, conduct heat well, have a controlled thermal expansion coefficient, be relatively lightweight, and resistant to corrosion and wear.
That's quite the list of requirements. And one of the big challenges is dealing with the heat, right?
Absolutely. The temperature difference between the piston crown, which is exposed to the burning fuel, and the piston skirt, which is in contact with the relatively cooler cylinder wall, can create significant thermal stress.
So how do they manage that heat?
Well, in smaller engines, some of the heat is dissipated through conduction to the cylinder liner and through radiation and convection to the crankcase air.
Okay, but what about the really big engines?
In those cases, you need some form of internal cooling.
Like-
They circulate either water or lubricating oil through channels within the piston itself.
So the piston has its own internal plumbing system.
Pretty much, yeah. And both water and oil have their pros and cons.
Like what?
Well, water is a better coolant, but it can lead to scale buildup and contamination if there's a leak.
Okay, and oil.
Oil cooling can be integrated with the main lubricating oil system, which is simpler, but oil isn't cooled quite as effectively as water.
Interesting. And you mentioned that the piston crown is actually papered.
Right, that's to account for the uneven thermal expansion. The crown gets hotter than the skirt, so it needs a bit more room to expand.
And how much clearance is there typically between the piston and the cylinder liner?
In large crosshead two-stroke engines, it's usually around 0.2% of the cylinder bore diameter.
So it's a very tight fit.
It has to be to maintain a good seal.
Okay, now let's move on to the cylinder liners. What can you tell us about those?
The cylinder liners are basically the replaceable sleeves that the pistons move up and down in.
And what are they made of?
Typically, they're made of high-grade cast iron with various alloys added to improve strength, wear resistance, and corrosion resistance.
Because they're exposed to pretty much everything, right?
Yeah, they see it all. High temperatures, high pressures, abrasive wear from the piston rings, corrosive wear from the combustion byproducts.
So how do they protect these liners?
Well, lubrication is key. They inject a special alkaline lubricating oil into the cylinders through multiple points called quills.
And this oil does what?
It reduces friction, neutralizes those corrosive acids, helps to seal the gap between the piston rings and the liner, and it helps to clean away any debris.
Okay, and I imagine they monitor the wear on these liners very carefully.
They do. They usually measure the bore diameter at various points every 6,000 to 8,000 operating hours.
And when do they replace them?
Generally, when the wear reaches about 0.6 to 0.8% of the original diameter.
Okay, so they're keeping a close eye on those liners.
Absolutely. You don't want those things to fail.
Now let's talk about the bearings. These are the components that allow all this rotational motion to happen with minimal friction and wear.
Right. Bearings are crucial for smooth operation.
So what are the key properties that these bearing materials need to have?
Well, they need to be strong under both tension and compression.
Okay, what else?
They need to conduct heat well to dissipate the heat generated by friction.
Right,
They need a high melting point so they don't fail under those high temperatures.
got it.
They need a high load carrying capacity to support all those rotating parts.
And?
And they need some ductility, meaning they can deform a bit without breaking.
Okay, so what kind of materials are used for these bearings?
The main materials are white metals, also known as Babbitt's metals. They're usually tin-based alloys.
And what's special about them?
They're great at absorbing small particles, and they have a very low coefficient of friction.
Okay, so they're tough and slippery.
Exactly. And modern bearings often use thin-walled steel shells with multiple layers of different alloys to get the best combination of properties.
Interesting. So we have the main bearings that support the crankshaft
Right.
and the connecting rod bearings that connect the connecting rods to the crankshaft.
Right, again.
And in two-stroke engines, we also have the crosshead bearings.
Yeah, those are the ones that connect the piston rod to the connecting rod.
Now, your materials mentioned that the crosshead bearings in two-stroke engines face some unique lubrication challenges.
They do, yeah.
What are those challenges?
Well, unlike the main and connecting rod bearings, which are rotating continuously, the crosshead bearing is oscillating back and forth.
So it's a different kind of motion.
Exactly, and it's also subjected to a very high unidirectional load during the power stroke.
Okay, and what's the problem with that?
It makes it harder to maintain a good oil film between the bearing surfaces.
So there's a greater risk of wear.
Exactly, especially in those modern high-performance two-stroke engines that are running at higher pressures.
So how do they address these challenges?
Well, they've come up with some clever designs.
Right.
They use continuous lower bearing shells without a split, which helps to distribute the load better.
Okay, what else?
They use special oil groove patterns to promote the formation of a stable oil wedge.
Right.
They use superfinished gudgeon pin surfaces to improve lubrication.
And of course, they make sure there's a constant and sufficient supply of oil to the bearing.
Absolutely, you can't skimp on the lubrication in those crosshead bearings.
All right, the last of the major structural components we need to discuss is the cylinder head. What's its primary function?
Well, the cylinder head is basically the lid on top of the cylinder. It seals everything up and forms the upper part of the combustion chamber.
It must be incredibly strong, right?
Oh yeah, it has to withstand those incredible pressures and temperatures generated during combustion.
And what else does it do?
It also houses a bunch of important components like the exhaust valves, the fuel injector, the starting air valve, the relief valve, and sometimes an indicator cock for measuring cylinder pressure.
It's a pretty busy place.
It is, yeah. It also has passages for the cooling water and sometimes for the intake and exhaust gases.
And I'm guessing there are some common problems that can occur with cylinder heads.
Yeah, they can crack from the thermal stress.
Okay, what else?
They can distort from uneven heating. The cooling water passages can get clogged with scale or deposits.
Right.
And they can suffer from corrosion and erosion from the hot combustion gases.
So they really take a beating.
They do, but they're designed to withstand a lot.
Okay, so the design of the cylinder head is different between two-stroke and four-stroke engines, right?
It is, yeah. In two-stroke engines, you usually have a single large exhaust valve in the center of the cylinder head.
Right?
And the scavenging ports are located in the cylinder liner itself.
Okay, and in four-stroke engines?
You have separate inlet and exhaust valves, and they're both located in the cylinder head.
Okay, that makes sense. Now, you mentioned that the exhaust valve, especially in a two-stroke engine, is a pretty critical component.
It is, yeah. It's working under some of the harshest conditions in the entire engine.
So what kind of challenges does it face?
Well, it's exposed to those extremely hot exhaust gases.
Right.
And those gases can be very corrosive, especially if the engine is running on heavy fuel oil.
So what do they make these valves out of?
They're usually made from special high-temperature alloys like Nimonic.
And are they water-cooled?
Often, yes, especially in large two-stroke engines.
And how do they operate?
They're usually hydraulically actuated, and their timing and controlled by a cam on the camshaft.
Okay, and what are some of the potential problems that can occur with these exhaust valves?
Well, they can suffer from corrosion and abrasion from the exhaust gases.
Right.
They can overheat if the cooling system isn't working properly.
Okay, and what else?
They can have problems with reseating properly, which can lead to leaks.
And that can obviously affect the engine's performance.
It can, yeah. And another problem is shrouding, where deposits build up on the valve seat and restrict the flow of gases.
So regular inspection and maintenance are crucial for these valves.
Absolutely. They need to be checked regularly and often have their seats ground to ensure a good seal.
Okay, we've covered the core engine structure and all those moving parts. Now let's shift our focus to the supporting systems that are essential for these engines to function properly.
All right, let's get into those systems.
And let's start with supercharging. Why is supercharging so important for marine diesel engines?
Well, it all comes down to efficiency and power output.
Okay, how so?
The amount of fuel you can burn in a cylinder is limited by the amount of oxygen available in the air.
Right.
And supercharging increases the density and pressure of that intake air.
So you can cram more air into the cylinder.
Exactly. And that means you can burn more fuel, which means more power.
Okay, and how do they achieve this increase in air pressure and density?
There are a couple of ways.
Like-
You have mechanical superchargers, like rotary blowers or scavenge pumps.
Okay, and those are driven by?
They're driven directly by the engine's crankshaft.
But they're not as common in modern engines, right?
Not really, no.
Why not?
They're not as efficient. They actually consume some of the engine's power to drive themselves.
Okay, so what's the more common method?
Turbocharging.
And how does that work?
It uses the energy in the engine's exhaust gases to drive a turbine. And that turbine is connected to an air compressor, which forces more air into the cylinders.
Clever. So they're actually using waste energy to boost the engine's power.
Exactly. And that make things even more efficient, they often use a charge air cooler.
What's that for?
It cools the air after they're compressed.
Why?
Because cool air is denser, which means you can pack even more oxygen into the cylinders.
I see. So they're really trying to optimize things.
Absolutely. Every bit of efficiency counts when you're talking about these massive engines and the amount of fuel they consume.
Now, your sources also mentioned different types of turbocharging systems, like constant pressure and impulse turbocharging.
Right, and those have different characteristics in terms of their efficiency at different engine loads and how effectively they scavenge the cylinders.
Okay, and there are also different types of turbines, right?
Yeah, you have axial flow turbines and radial flow turbines. They're just different designs for extracting energy from the exhaust gas.
Okay, and I imagine they clean those turbochargers regularly.
Oh yeah, they usually do water washing to remove any deposits that build up on the compressor and turbine blades.
Okay, let's move on to the fuel system.
All right, the fuel system is what keeps the whole thing running, literally.
And we know that most large ships run on heavy fuel oil, or HFO.
Right, it's the most economic fuel for these big vessels.
But it's not the easiest fuel to work with, is it?
No, not really.
Why not?
Well, it's extremely viscous,
Meaning?
meaning it's very thick, almost like tar at ambient temperatures.
So what's the problem with that?
It's difficult to pump and atomize for combustion.
So what do?
They have to heat the whole fuel system.
From the storage tanks to the injectors?
The whole thing, yeah.
And how do they heat it?
They use thermal insulation called lagging, and they run steam or electric heating elements along the fuel lines and inside the tank.
So they're basically keeping the fuel hot enough to flow properly.
Exactly. But they also need to be able to switch over to distillate fuels like marine diesel oil when necessary.
When would they do that?
When they're maneuvering in port, for example.
Okay, or when the main engine is shut down.
Right.
So it's a bit of a balancing act.
It is, yeah. You have to keep that heavy fuel oil hot enough to flow, but you also need to be able to switch to a lighter fuel when needed.
Okay, so once that heavy fuel oil is heated and flowing, how is it actually injected into the cylinders?
Well, that's the job of the fuel pump and the fuel injectors.
And what exactly does the fuel pump do?
It has several important functions.
Like?
It meters the exact amount of fuel needed for each combustion cycle.
Okay, and what else?
It pressurizes the fuel to an incredibly high level so it can be atomized properly.
And?
It injects the fuel at the precise moment in the engine cycle for optimal combustion.
And finally?
It ensures a clean cutoff of the injection so there's no dribbling.
Okay, so it's a pretty precise piece of equipment.
It has to be. And your sources probably mention different types of injection systems.
Like common rail systems, right?
Right. Those use a high-pressure fuel manifold that's shared by all the cylinders.
Okay, and the injection is electronically controlled.
Exactly. And then you have unit injection systems, where each cylinder has its own dedicated pump and injector unit.
And those are?
Those are very common in marine engines.
Okay, and what about the actual injection pumps themselves? What types are there?
Well, there's the jerk-type pump, which uses a plunger with helical grooves and a spill port to control the amount of fuel injected.
Okay, and what's the other type?
The valve-controlled pump, which uses pushrod-operated valves to control the fuel flow.
And the timing of the injection can be adjusted, right?
Absolutely. They use variable injection timing systems, or VIT, to optimize combustion pressure at different engine loads and with different fuel qualities.
Especially important when you're dealing with heavy fuel oil.
Very important, yeah.
Okay, so the fuel pump does its job, and then the fuel goes to the injectors.
Right. The injectors are what actually spray the fuel into the combustion chamber.
And what's important about their design?
Well, they need to atomize the fuel very finely so it burns efficiently. And they need to create a spray pattern that ensures good distribution of the fuel throughout the combustion chamber.
And cooling is critical, right?
Oh, yeah. Those injector nozzles are exposed to incredibly high temperatures.
So if they overheat,
You can get all sorts of problems, like the fuel boiling at the nozzle tip.
okay, and
You can get carbon deposits forming on the nozzle,
which can.
block the spray holes, and reduce the efficiency of the injection.
So how do they prevent overheating?
Well, some designs use hydraulically operated fuel valves that have a constant flow of heated, heavy fuel oil circulating around the nozzle tip.
So they're basically keeping the nozzle bathed in hot oil.
Exactly. It helps to keep the temperature stable and prevent those carbon deposits from forming.
Okay, and what are some of the common problems that can occur with injectors?
Well, as we said, they can overheat.
Okay.
They can dribble fuel after the main injection.
That,
They can get clogged with carbon deposits. And they can have problems with the spring pressure, which can affect the timing and pressure of the injection.
so they need to be inspected and maintained regularly, just like everything else.
Absolutely. You want to make sure those injectors are in tip-top shape.
Okay, let's move on to the cooling water system.
All right, keeping those engines cool is essential.
I'm guessing things get pretty hot in there.
Oh, yeah. You've got the heat from the combustion itself, and you've got friction between all those moving parts.
So what happens if the engine overheats?
Well, the materials can lose strength, which can lead to catastrophic failures.
Yikes.
And you can also get excessive thermal stresses, which can warp and crack components.
So they obviously take cooling very seriously.
They do, and they use a closed circuit system with fresh or distilled water to cool the engine.
Why not just use seawater directly?
Seawater is very corrosive and tends to form scale deposits.